All right, so now we're going to take a look at root finding algorithms in R. We'll start with the most accessible one, which is uniroot. This makes use of the Newton-Raphson algorithm for finding the root of a function. The arguments are that we put in the function. Okay, this must be defined, by the way, as a function, and the interval to be searched over, so this would be across the real line. And then there can be additional arguments passed into the uniroot function that would control certain variates within f. So particularly if you need to set other parameters within your function that you've defined, you can pass them in here within the ... This will only return one root. It does use the Newton-Raphson algorithm, which can be, I actually usually use the secant algorithm, which can be a little bit slower than Newton-Raphson, but is more stable for lots of different settings. In lots of different settings. If multiple roots exist, you're going to need to go with something else as well. So let's take a look at an example here. So here we've defined a function. So notice f is defined as a function. This is just a regular user-defined function like we've done many times. What is the variable? It is x. Okay, so we've got this equation involving x. We can plot the function just to make sure we understand it. I think this would be useful for you to see, actually, so let me take a look at this and run through this with you in just a moment. And then we can look at how an interval from 0 to 2 might look and kind of guesstimate what we think the 0 may be at that point. Then we'll take a look at the root between that interval 0 to 2 and see what the uniroot solution is. It will only, then we're going to look at -3 to +3, and it will only return one root even if we think there could be multiple roots within the interval. Finally, the endpoints need to be of opposite sides. So we're going to take a look at what happens if we run this last command. All right, so first of all, here's the function plotted. We can see that there's 3 roots to this function. Of course, if we look at the interval between 0, if you just imagine a vertical line drawn here, and 2, we do see one unique root to that segment of the function. So let's take a look at how that would play out. So running just this first piece of code for uniroot where we find the root between 0 and 2. And indeed, we do see the root right there. This is at 0.87, more or less. Let's take a look again. Between 0 and 2, right here, we would find the root. It's saying it's about 0.87, which looks about right if you eye it. All right. So we could also find the root between -3 and +3. Notice that would span this and this. So let's see what happens. So we get back feedback that our root is a -0.69, so about 0.7 really. So let's see, -0.7, it's picking up the first one, the lowest one numerically. Of course, this is also a root. The 0.87 is also a root. So we need to be aware of that. That can be misleading if you don't plot your function first. Finally, we can run it between 1 and 2. Okay, take a look before we run this. F of 1 and f of 2 can be evaluated. If you look at the end result, we get positive values for both f of 1 and f of 2. And as you know, you need opposite signs for your f values in order to find the 0. There's no 0 between these points. So let's take a look, and we get back an error message saying that the f values are not of opposite sign. Okay, so again, this just points, these last 2 examples really just point out the necessity of plotting your function first so that you do not make silly mistakes or not understand why you get an error such as f must be of opposite sides. Continue now. Let's take a look at a statistics example. Suppose we want to simulate n equal 100 observations. The event times follow a Weibull distribution with shape and scale parameters 2 and 1. The censoring times C are distributed uniformly from 0 to tau. So this is the typical setup that you might look at in survival modeling. Then the observed time is going to be the minimum of T and C. Again, what is T, the event time, and C is the censoring time. Okay, so the time it gets cut off, in other words, and it's got to be the minimum of those two. Assume that C and T are also independent. That's a core assumption of the model. The value of tau is chosen to give you the desired censoring rate. So this must be optimized in order to find the rate at which we want to censor our observations. So for example, if we want to censor 25% of our observations, then the probability of censoring, meaning C less than T, must be 0.25, or we set it at 0.25. So now we need to choose tau so that that probability of C less than T is equivalent to 0.25. That actually involves minimizing this quantity and solving for the unknown quantity tau that will provide this proportion of censoring proportion. Okay, so we're going to need to first use the integrate function, which we've already gone over, and then the uniroot. So we're going to make use of both here. So first we use the function here. Notice S is going to be defined as a function of T, okay? 1 minus the cumulative distribution function of the Weibull with A and B set, and it's a function of T. Don't worry too much where this comes from. You need to know a little bit about survival modeling to know it. Just know that this is a function of T here. Then we're going to integrate S from 0 to tau. So notice that follows our limits of integration here from 0 to tau. We're going to recover the value. So when we do $ value here, that just gives us back the integrand of that result of this thing right here. We have to be careful of this thing because notice we're dividing that integrand by tau because of that ratio out in front, 1 over tau. And then we're going to subtract off the percentage that we want censored, which is 0.25 in this case. Then we will return our uniroot of f between the interval 0.001, so just very, very close to 0 because we can't go to 0, and up to 100, and we're going to get back the root. Okay, so that is going to give us our upper uniform censor upper bound. Okay, if we were to run this this function, uniform censor upper bound, notice, by the way, the function gets defined inside that other function, and then the root of our function f is returned as a value of our uniform censor upper bound here. Okay, so those are our arguments that go into this, then it feeds into this. This gets optimized using, or we find the root using uniroot, and then that gets returned. So then we can save that root within tau and then use it for evaluating. And here, this is really, I'm not going to go over this, but this is just verifying that this value of tau does indeed provide. I was jumping ahead of myself just a moment ago, and now we are ready for optimization procedures within R. There are several functions within R for optimization. The optim or optimize are good, easy to use. Optimize is pretty simple. It's a one-dimensional optimization. A Hessian matrix does not get computed or used. Finally, optim is this is the one I use most of the time because it's most flexible and provides more functionality than optimize. You can do constrained optimization using this function, nonlinear optimization, and then you can use port routines, which I don't usually use this kind of method and am not very familiar with it. Okay, so these functions are each going to use a different algorithm, and they're all a little bit different, so just be aware of that. If you want to maximize a function, then you just multiply your objective function in your gradient by -1. So don't get confused thinking I need to look for a separate set of functions for maximization problems rather than minimization problems. You can use them for both. Okay, there's also a lot of packages for this. In class also, I should tell you, like, I've written, with regard to optimization and I have to say root finding, I've written my own version of the secant algorithm. And so that is another option for you with both of these. If none of these options suffice, then write your own. It's really not hard to write, for example, a secant algorithm. Okay, so one-dimensional optimization, I'm just going to go over the basic idea. You enter your function that needs optimizing, your upper and lower bounds, that interval, and then if you want to find the maximum, you can set that as true. So this is the one case, actually, you can just default the false of finding this is a minimization setup right here and make that true, and you got a maximization algorithm there. Okay. You cannot specify the gradient to assist with your optimization is the really big downside. Let's look at some applications, though. I think I'm gonna take a break here. Why don't you, on your own, run through these functions, and then we'll come back and look at some of the results. Notice that this uses the same function we had just used before, so it's really going to be easy to go ahead and make sure that you can make use of this application of the optimize function.